You know, when you're making a massive, like industrial-sized pot of soup and you really want to know if it needs more salt, you don't sit there and drink the entire gallon.
No. Well, that would be highly inefficient.
Hmm.
And it would probably ruin your dinner, not to mention your sodium levels for the entire week.
Right, exactly. You take a spoon, you give the pot a really good, vigorous stir, and you just taste one single spoonful.
Yeah.
And if you stirred it correctly, that one tiny spoonful tells you, absolutely everything you need to know about the entire vat. You don't need to consume every single drop to understand the whole.
It's the perfect metaphor, honestly, for what we're doing today.
Because today we are doing a deep dive into the scientific equivalent of that spoonful. We're getting into the sometimes controversial, but always vital world of how we abstract the truth from massive populations without actually talking to every single person.
Right. And our mission today, tailored specifically for you, our listener, is to explore the 30 core principles of sampling methodology.
Straight from the foundational curriculum in biomedical research.
Exactly. But we aren't going to just, read out definitions and force you to memorize them. We're going to look at the actual mechanical gears of these concepts.
Because we want to understand how researchers can look at a group of, say, 1,000 people and confidently, mathematically speak, for a billion.
Yeah, and we'll do that by working through 30 specific conceptual questions, kind of decoding the exact scenarios researchers face out in the field.
So I'll pause the scenario or the problem, and we will figure out exactly what the right approach is, and more importantly, the underlying logic of why it actually works.
Because, going back to your analogy, if you don't stir the soup right, your spoonful is going to lie to you.
It totally will. So let's start at the absolute bedrock. If I want to make a claim about a massive group of people, say, all adults with diabetes in an entire country, I obviously can't track down millions of individuals.
No, you can't.
So what is the formal term for the process by which some members of a population are selected as representative of the entire population?
So the term for that process is simply sampling.
Sampling. Just plain old sampling.
Right. It seems like a super basic definition, but the philosophical shift it represents is actually massive. For most of human history, governments relied on censuses.
Like the Roman Empire trying to count every single citizen.
Exactly. For tax purposes, mostly.
Right.
It was this exhaustive, literal head count. But sampling is the mathematical realization that we just don't have to do that. We extract a representative slice, and we use that slice to project reality onto the whole.
Which naturally brings up the question of motivation, right? Like, why do we do this? Aside from it just being annoying or difficult to track everyone down, what is the primary thing that sampling achieves?
Well, the primary thing it achieves is the efficient utilization of resources.
Resources being what? Time and money.
Time, money, and human labor. The holy trinity of research.
I feel like efficient utilization is almost underselling it, though. If the alternative to sampling is a full census where you evaluate every single individual, that's not just inefficient, it's often flat out impossible.
Oh, completely.
Like, the U.S. Census happens only once a decade. It costs billions of dollars, requires hundreds of thousands of temporary workers, and it still takes years to fully process the data.
Right. Imagine trying to run a medical study on a new blood pressure medication using a census approach.
You'd never finish.
Exactly. By the time you finish collecting the data from every single hypertensive patient in the country, a whole decade would have passed. The disease landscape would have changed, the medication might be totally obsolete, and, well, you would have bankrupted your research institution.
So efficient utilization of resources is really what makes real-world, continuous scientific observation physically possible in the first place.
Yes. It allows us to get actionable results fast enough to actually help people.
Okay, so we agree we have to sample. But you can't just walk outside your laboratory, grab the first 10 people you see on the sidewalk, and call it a day.
Please don't do that.
Right. You need a structured starting point. If you want to sample people fairly, you need a master list. So what do we call the list of all individuals in the study population from whom study participants in research are to be selected?
That master list is known as the sampling frame. And this is a concept that researchers obsess over, and for really good reason.
It's basically the invisible scaffolding of the entire study.
It is.
I always think of the sampling frame like the ultimate guest list for a highly exclusive VIP event. If your name is not on that physical master list, the bouncer doesn't know you exist.
That's a great way to put it.
You cannot be randomly picked to get a VIP pass. If a researcher doesn't have you on their sampling frame, you have exactly zero chance of being in the study.
That is a brilliant way to visualize it. Let's say you want to randomly select 500 students from a university to assess their mental health. You don't just wander the library tapping people on the shoulder.
No, you go to the registrar's office.
Exactly. You go to the registrar's office and you get a literal, exhaustive spreadsheet of every single student currently enrolled. That spreadsheet is your sampling frame.
But wait, what if the registrar's list is flawed? Like, what if their database just hasn't been updated to include the 200 transfer students who literally just arrived this semester?
Then your sampling frame is broken.
Yeah.
And by extension, your entire study is compromised before you even draw a single name.
Because those transfer students have no chance of being picked.
Right. If they are systematically excluded from the sampling frame, they mathematically cannot end up in your sample. Your final sample won't be truly representative of the university. This is actually why building a robust, accurate sampling frame is often the most difficult, tedious part of field research.
It reminds me of that infamous 1936 Literary Digest poll.
Oh yes, a classic disaster.
Right. They wanted to predict the presidential election between Alf Landon and FDR, and they mailed out millions of mock ballots. But their sampling frame, their master list, was built from telephone directories and country club memberships.
And in 1936, right in the middle of the Great Depression, who had telephones and country club memberships?
Mostly wealthy individuals.
Exactly. Wealthy individuals who leaned heavily Republican. The magazine predicted a landslide victory for Landon.
But in reality, FDR won in one of the biggest landslides in American history.
Because the Literary Digest sampling frame essentially excluded the working class. So their sample, despite being massive, I think they had millions of responses, was completely invalid.
That perfectly illustrates why the methodology matters so much more than just the raw size of the sample. And the reason we care so much about this list and this strict randomness is grounded in pure mathematics. Let me throw a true or false statement at you.
Go for it.
Commonly used statistical inferences have the assumption of a probability sample. Is that true or false?
That is absolutely true. And this is really the engine under the hood of everything we're talking about in this deep dive.
Unpack that term for me. Statistical inferences. Because when I read a scientific paper, it usually says something like, we are 95% confident that the true prevalence of this disease in the population is between 12% and 16%.
Right.
That confidence interval, that calculation, that's the inference, right?
Precisely. You are inferring a truth about the massive population based on the tiny sample. But you can't just make up that 95% confidence number. It is generated by complex statistical formulas.
Stuff like the normal distribution, the central limit theorem.
Standard error calculations, exactly. All that heavy mathematical machinery.
And those formulas are very rigid about their inputs, I assume.
Extremely rigid. Those statistical laws literally assume at a foundational mathematical level that every single person in your sample had a known non-zero probability of being selected.
Wow.
Yeah. If you didn't use a probability sample, if you just asked your friends or polled people who happen to follow you on social media, the statistical math actually breaks down. It becomes completely invalid garbage.
So even if the software spits out a number, it's lying to you.
The formulas will always spit out a number if you plug data into software, but the number is a lie. So yes, it is true that valid statistical inference demands a probability sample.
Okay, so if we want to use the heavy machinery of statistics, we have to play by the rules of probability. And the most famous gold standard rule in the book is the one everyone thinks of when they hear the word random.
Right, simple random sampling.
Exactly. If a sampling method is based strictly upon an equal chance of selection for everyone, what is it called? Well, you just gave it away.
I did, sorry. It's called simple random sampling. It's the purest, most undiluted form of probability.
And just to hammer this home because it's so critical, in simple random sampling, what exactly is the probability of selection for each individual?
It is exactly equal. No individual has a higher or lower chance of being picked than anyone else in the sampling frame.
It's like writing everyone's name from your sampling frame onto identical slips of paper, putting them into a giant, perfectly mixed drum, and pulling out names blindfolded.
That's the exact conceptual model, yeah.
So if there are 1,000 people on your list and you need 100 of them, everyone has exactly a 10% chance of being selected.
Right. Though obviously today, we don't use slips of paper. We use computer-generated random numbers. We assign every person on the frame a number from 1 to 1,000, and an algorithm generates 100 truly random numbers. Those are the people you study.
But human beings are notoriously bad at understanding randomness.
We really are.
We constantly try to inject our own judgment. So let me pose a scenario to see what simple random sampling is not. If a statement claims that purposive sampling is a type of simple random sample, is that true or false?
That statement is unequivocally false.
Wow.
So if you were looking for the false statement in a list of sampling traits on an exam, the claim that purposive sampling is a type of simple random sample is the one you need to flag.
Why are they so incompatible? What is purposive sampling doing that breaks the rule?
The word purposive implies that a human being is making a subjective, deliberate choice with a specific purpose in mind. Simple random sampling is blind. Purposive sampling is staring right at you and judging you.
Huh. Give me an example of how a researcher might accidentally or intentionally do this.
Sure. Imagine a doctor trying to establish the quote-unquote typical recovery time for surgery. They might look at their patient roster and say, well, patient A is a bit too old and patient B had weird complications, but patient C is a very typical average patient. I'll purposely pick patient C for my study.
I can totally see the temptation there. The doctor thinks they're helping the study by picking a clean example.
Exactly. They think they're reducing noise in the data. But the moment human judgment or specific intent enters the selection process, it's no longer blind, and the probabilities are no longer equal
Patient C basically had a 100% chance of being picked.
because the doctor liked them. And patient A had a 0% chance because the doctor excluded them based on a personal definition of what typical means. You have totally destroyed the probability math. Purposive sampling and simple random sampling are polar opposites.
Okay, so simple random sampling, let's just call it SRS, sounds perfect in theory. It's blind, it's fair, it's entirely mathematical. But I have to push back a little here.
Okay.
Is it really flawless? Because if fairness is the only goal, what about representation? If someone claims that SRS always achieves best representativeness, is that a true statement?
No, that is an incredibly common misconception. If you see a claim stating that SRS always achieves best representativeness, you should immediately identify it as false. The correct answer to what SRS does not do is that it always achieves best representativeness.
Wait, hold on, I'm confused. If the process is completely random, perfectly blind, and mathematically fair, shouldn't the outcome be perfectly representative of the population?
You would naturally think so, but we have to respect the chaotic reality of chance. Think about flipping a perfectly balanced coin. The process is perfectly fair, 50% chance of heads, 50% chance of tails.
Right.
If you flip that coin 100 times, you expect 50 heads and 50 tails. But is it guaranteed?
Oh, no, obviously not.
Right. By pure mathematical luck of the draw, you could end up flipping 80 heads and 20 tails. It's rare, but the laws of probability absolutely allow for it.
Oh, I see. So translate that to a human population for me.
Let's say your sampling frame is a town with exactly 50% men and 50% women. You put all their names in a giant hat and draw 100 names at random. By the exact same chaotic luck of the coin flip, you could end up pulling the names of 80 men and only 20 women.
Wow. Okay, so the process was entirely fair. Everyone had an equal chance of being picked. But the result, the actual sample you have to work with in your laboratory is horribly skewed. It doesn't look like the town at all.
Exactly. It is fair, but it is not perfectly representative.
SRS usually does a good job, especially if your sample size is massive, but it is never a guarantee. Chance can hand you a bizarre, unrepresentative outlier. Therefore, claiming it always achieves best representativeness is fundamentally false.
That is a massive conceptual breakthrough for me. Because if simple random sampling has this built-in vulnerability to random chaotic luck, and because randomly generating numbers and tracking down people all over a city is a logistical nightmare, researchers had to upgrade their methods, right?
Absolutely did. They needed tools to force better representation and make field work less painful. And that is exactly what drove the evolution of the next tier of probability sampling: systematic and stratified techniques. These are like the absolute workhorses of modern field epidemiology and polling.
Yes, they are.
Let's unpack systematic sampling first because it sounds so brilliantly pragmatic. Suppose a researcher wants to draw a sample from sequentially numbered houses on a street. They pick a random starting point and then they walk down the street and select every sixth house. What kind of sample have they drawn?
That is the textbook definition of a systematic sample. The key indicator is always that sequence and that regular interval, the every sixth house part.
Let's actually walk through the logistics of this because researchers have to calculate this stuff before they leave the office. Imagine a scenario where a researcher is looking at a neighborhood with 5,000 houses. They know they have the budget and time to obtain a sample of 50 houses. To do a systematic random sample, what will their sampling interval be?
The sampling interval in that specific scenario will be 100. And the math to get there is beautifully straightforward, which is why researchers love it.
You literally just take the total population and divide it by the sample size you want, right?
Exactly. You have 5,000 houses, you divide by 50. The result is 100. That number, 100, becomes your stepping stone.
So to make it random, I don't just start at house number 1. I use a random number generator to pick my very first house somewhere between 1 and 100. Let's say the computer spits out the number 42. I go to house 42. From there, I just add the interval. The next sample is house 142, then house 242, then 342, all the way to the end of the neighborhood.
Exactly. Now think about why that is so superior for field workers compared to simple random sampling. If you used SRS in a neighborhood of 5,000 houses, your random numbers might be 14, 4999, 15, 3016.
Oh my gosh, you would be zigzagging wildly across town. You walk 5 miles to the edge of town, then walk 5 miles back for the very next house. It would take weeks just to walk it.
Right. With a systematic interval, you are moving in a logical geographic progression. You walk down the street, count to 100, knock on the door, count to 100, knock on the door. It saves immense amounts of time and shoe lever.
But I'm going to play devil's advocate here.
Okay.
It saves time, sure, but does it actually improve the science? I mean, which statement is generally true when comparing systematic random sampling to simple random sampling?
What is statistically true is that the selected sampling units are likely to be more representative than simple random sampling.
Okay, defend that. Why is my every 100th house better than pure blind randomness?
It goes right back to the flaw we just exposed in simple random sampling, the 80 heads, 20 tails problem.
Right.
In a geographic context, pure chance could easily randomly select 50 houses that all happen to be clumped together on the wealthy, newly developed east side of town, completely ignoring the older, lower-income west side.
Because randomness doesn't care about geography. Randomness doesn't know where the train tracks are.
Exactly. Randomness can clump. Systematic sampling forcibly prevents clumping. By stepping evenly through the population, every 100th house, you guarantee that you pull a little bit from the beginning of town, a little bit from the middle, and a little bit from the end. You forcibly spread your sample across the entire physical space.
So you automatically capture the wealthy neighborhoods, the middle-class neighborhoods, and the poor neighborhoods simply by marching evenly through them.
Correct.
Okay, you mentioned playing devil's advocate earlier. Is there a trap here?
There is one very specific danger with systematic sampling that researchers have to watch out for. What if the population has a hidden periodicity?
Periodicity, like a repeating pattern.
Yes. Imagine a scenario where a city developer built blocks of identical houses, and exactly every 10th house is a larger corner lot, which happens to be much more expensive.
Okay.
If your sampling interval happens to be 10 and your random start puts you on a corner lot.
Oh, wow. You would end up sampling only corner lots for the entire study.
Exactly. Your entire sample would be exclusively the wealthiest people on the block, without you even realizing it.
Because your interval accidentally synced up perfectly with the neighborhood's architecture. That's wild.
It's a rare trap, but it illustrates why researchers must understand the underlying structure of their sampling frame before they decide on an interval. But, barring those hidden patterns, systematic sampling is vastly superior for ensuring geographic spread.
Okay, so systematic sampling solves the geographic clumping problem. But what about the demographic clumping problem? What if I want to make absolutely sure I don't get that bizarre 80 men, 20 women split? How do we force demographic representation?
That is where stratified sampling comes into play. And it is arguably the most powerful tool in the epidemiologist's toolkit.
Let's look at a clinical example. Suppose a researcher is studying lung cancer. Based on the number of cigarette smoke per day, the researcher divides the population into 3 distinct risk groups: low risk, moderate risk, and high risk. Then the researcher draws a random sample from each of these risk groups independently. What kind of sample has been created?
That researcher has created a stratified sample. The word strata essentially means layers or categories.
I like to visualize this like an enormous bowl of M&Ms.
Naturally.
Right. If I just grab a blind handful, a simple random sample, I might get a handful of mostly brown M&Ms and completely miss the blue ones just by chance. But if my scientific study absolutely requires me to test an equal amount of red, blue, and green M&Ms, what do?
You intervene before the sampling starts.
Exactly. I dump the bowl on the table and manually sort the entire population into color-coded piles: a red pile, a blue pile, a green pile. Those piles are my strata. Then, and only then, I randomly pick 5 M&Ms from within the red pile, 5 from the blue pile, and 5 from the green pile.
It's a perfect analogy. And translating that back to the clinical example, The researcher manually sorts the population into the 3 smoking risk piles first. Then they randomly sample within those piles.
Which guarantees representation.
Right. This guarantees that you have sufficient representation of heavy smokers, moderate smokers, and light smokers. Chance is no longer allowed to accidentally ignore one of those groups.
But wait, if I am manually interfering and sorting people into piles based on their traits, doesn't that break the sacred rule of probability? Like, look at this claim. In stratified sampling, the probability of a participant being selected is unknown. Is that true?
No, that is completely false. If you see a claim that the probability of a participant being selected is unknown regarding stratified sampling, you should flag it as the false statement.
Explain the math there. How do we still know the probability if we manipulated the groups?
Because the manipulation stops at the sorting phase. Once you have your strata, your piles, the actual selection from within that pile is still entirely random. It's conditional probability.
Okay, give me numbers.
Let's say your high-risk smoker stratum contains 1,000 people. You decide you need 100 people from this specific stratum. You use a random number generator to pick those 100.
So inside that specific pile, everyone had exactly a 10% chance of being picked.
Precisely. The probability is mathematically known and perfectly documented. You haven't broken the rules of probability. You have simply applied them in smaller, contained arenas. This is why stratified sampling allows us to use all the heavy statistical machinery we talked about earlier.
Which leads directly into why this method is so beloved for studying diversity. If a test asks which sampling method ensures that valid conclusions can be drawn about different subgroups in a population, the answer has to be stratified, right?
Absolutely. A stratified random sample is the only method that provides an ironclad guarantee that minority subgroups will be represented with enough statistical power to draw valid conclusions.
Break down that concept of statistical power for me in this context.
Sure. Let's imagine you are studying a rare autoimmune disease, and you suspect it affects a specific ethnic minority group differently. However, that ethnic group only makes up 5% of your city's total population.
Okay.
If you do a simple random sample of 1,000 people across the whole city, you might randomly pick only 40 or 50 people from that ethnic group.
And 40 people isn't enough data to draw a solid scientific conclusion about how a complex disease operates. The margin of error would be massive.
Exactly. You lack the statistical power to make a claim about them. But if you stratify by ethnicity first, you can employ what is called disproportionate stratified sampling.
Disproportionate. Okay, what does that mean?
You look at that 5% minority stratum and say, I am going to intentionally oversample this group. I'm going to randomly pull 200 people from this specific pile, even though they are a tiny part of the total city.
So you force the math to give you a large enough sample of that specific subgroup to actually learn something meaningful about them.
Yes. You mathematically weight the results later to fix the overall city average. But by stratifying, you ensured that the subgroup was not invisible. You ensured valid conclusions could be drawn about them.
But there is a mathematical catch to this, a fundamental law that these sorts of exams love to test. Consider the statement. In stratified random sampling, precision improves with low numbers sampled in each stratum. Is that a true or false statement?
That is undeniably false. The claim that precision improves with low numbers sampled in each stratum defies the basic laws of statistics.
Why? What is precision, mathematically speaking?
Precision is a measure of how tight your confidence interval is. How certain are you of your number? The fundamental law, known as the law of large numbers, dictates that as your sample size increases, your sample mean gets closer to the true population mean.
So more data equals less uncertainty. Always.
Always. The standard error of a statistic is calculated by dividing the standard deviation by the square root of the sample size. As the sample size, the number in the denominator goes up, the error goes down.
So precision improves.
Yes. So if a statement claims that precision improves with low numbers, it has the math completely backward. In any stratum, you want as high a number as your budget will possibly allow.
Okay, let's zoom out a bit. We've built these incredible tools. Simple random sampling is mathematically pure. Systematic sampling makes walking a neighborhood a breeze. Stratified sampling guarantees minority representation. These are fantastic.
They are, but they all share one fatal flaw when you try to scale them up to a massive level.
Right. Section 1 told us that all of these probability methods require a sampling frame, a master list of the entire population.
Yes.
What if you are an epidemiologist for the World Health Organization and you are tasked with finding the malaria rate in an entire nation, say a country of 50 million people with heavily rural, unmapped territories?
You're in trouble.
Exactly. You do not have a giant master list of 50 million names. It doesn't exist. So you can't do simple, random, systematic, or stratified sampling on a national scale.
Which brings us to the ingenious solutions of cluster and multi-stage sampling. This is where researchers have to get incredibly clever with how they define the physical world. Let's tackle cluster sampling first.
Okay.
I'll give you a premise. All of the following are true regarding cluster sampling, except E1. The false claim is that it needs a complete list of units.
Wait. The answer is that the claim it needs a complete list of units is the false exception.
That's right.
But we just spent the first 20 minutes establishing that without a complete list, a sampling frame, you can't do probability sampling. Have we just thrown the rules out the window?
We haven't thrown the rules out. We've just changed the definition of a unit.
How so?
This is the absolute genius of cluster sampling. In simple random sampling, the unit is an individual human being. And yes, making a master list of 50 million individual humans is impossible. So in cluster sampling, we redefine the primary sampling unit.
So the unit is no longer a human.
Right. The unit is a village, or a school, or a city block.
Ooh. Oh, that changes everything. I can't make a list of 50 million people, but I can absolutely ask the government for a list of all 1,000 villages in the province.
Exactly. Your sampling frame is now a list of clusters. You randomly select, say, 30 villages from that list. Then, your research teams physically travel to those 30 villages, and they test every single person living inside those specific boundaries.
Because we're sampling massive groups rather than individuals, we completely bypass the need for a national citizen registry.
Yes. So it is exceptionally false to say that cluster sampling needs a complete list of all individual units.
That is a staggering logistical workaround. But it has to rely on a very specific assumption about how humans live, right? Let's look at the theoretical underpinnings. If a question asks to identify the false statement about cluster sampling, and one of the options is variability between clusters is assumed to be high, is that true or false?
That statement is false. The claim that variability between clusters is assumed to be high is a total inversion of the mathematical assumption required for cluster sampling to actually work.
Okay, we need to dive deep into this. What do we mean by variability between versus variability within?
This gets into the concept of intra-class correlation. For cluster sampling to be mathematically valid and representative, we have to assume that one randomly selected village is roughly generally similar to another randomly selected village in the same region.
Meaning Village A has a mix of farmers, merchants, kids, and elders. And Village B also has a mix of farmers, merchants, kids, and elders.
Precisely. We assume that the overall profile of the villages is basically similar. Therefore, the differences, the variability between the clusters, is assumed to be low.
Let me push back on that. What if that's not true? What if Village A is a wealthy mining town and Village B, just 2 miles down the road, is a completely impoverished agricultural settlement? The variability between them would be massive.
If the variability between them is massive, cluster sampling becomes incredibly dangerous. Because remember, you are only picking a handful of villages and totally ignoring the rest.
Right.
If Village A is completely unique and it doesn't get randomly selected, your final data will be missing a massive, unique piece of the puzzle. Your results will be heavily skewed.
So the math relies on the idea that missing Village A isn't a big deal because Village B will give us roughly the same kind of data anyway, low variability between.
Exactly. Conversely, we assume that the people inside any single village are incredibly diverse. We assume the variability within the cluster is high. You want a village to be a microcosm of the larger society.
So the exam question tries to trick you by flipping these concepts. It claims variability between clusters is assumed to be high.
Which is definitively false.
That is fascinating. It's almost a philosophical statement about human geography. But let's look at the physical reality again. Even with cluster sampling, traveling to 30 villages and knocking on every single door inside them is still a colossal amount of work.
It really is.
Testing an entire village of 3,000 people takes weeks. Can we break this down even further?
Yes, we can. When a cluster is still too big to handle, we introduce the concept of nesting. This is multi-stage sampling.
Let's use a real-world epidemiological example here. Imagine a study trying to measure the prevalence of fluorosis, a disease caused by too much fluoride in the drinking water across an entire massive district. The researchers sample towns first. Then, from those selected towns, they draw a sample of specific wards. Finally, from those selected wards, they draw a sample of individual households. What is the type of sampling used here?
That nesting bell approach is exactly what we call multi-stage sampling.
It's literally like zooming into a digital map, step by step.
It really is.
Yeah.
Stage 1, the primary sampling unit. You get a list of the 50 major towns in the district. You randomly select 5.
Okay, zooming in.
Stage 2, the secondary sampling unit. You completely ignore the 45 towns you didn't pick. For the 5 towns you did pick, you get a list of their municipal wards. You randomly select 3 wards per town.
Zooming in again.
Stage 3, the tertiary unit. For only those 15 selected wards, you send someone out on a bicycle to map out the physical streets and make a list of households. Then you randomly pick 20 houses per ward.
And the staggering beauty of this is revealed in its advantages. If an exam asks for a primary advantage of multi-stage sampling, it's that it circumvents the master list problem again, right?
Yes. A core advantage is that it does not require a complete list of the total population.
Because at no point did anyone sit down and try to write out every household in the district.
Never. You only ever had to create a physical list of houses for the tiny specific geographic wards you zoomed in on during stage 3.
Exactly. And that flows directly into the ultimate truth about this method. If asked to identify a true statement about multi-stage sampling compared to simple random sampling, what is the undeniable practical reality?
Well, the reality is that it saves resources as compared to simple random sampling. And honestly, saves resources is the understatement of the century.
It's the difference between a study being possible versus impossible.
Literally. If you attempted simple random sampling for that district-wide fluorosis study, you would first have to spend 5 years and millions of dollars mapping every single house in the entire district just to build your sampling frame. Multi-stage sampling allows researchers to parachute into specific zones.
It really marries the mathematical rigor of probability with the crushing constraints of real-world budgets.
It does. This is the exact framework used by massive global initiatives, like the demographic and health surveys conducted across Africa and Asia.
Okay, let's take a breath.
Good idea.
We have built an incredible, logically bulletproof toolkit. We have simple, random, systematic, stratified, cluster, and multi-stage. These methods are like the Avengers of epidemiology.
I like that.
They are rigorous, they rely on probability, and they conquer real-world logistics. But now we have to talk about the dark side.
Ah, yes, the dark side.
What happens when researchers have no budget, no time, or they're just structurally constrained? We leave the realm of probability and enter the murky, dangerous waters of non-probability sampling.
This is where we must separate rigorous, generalizable science from anecdotal observation. And it begins by correctly categorizing our tools.
Let's do a quick sorting exercise. If a question asks which methods are used in probability samples, and the options include stratified, multi-stage, and cluster, the answer is all of them, correct?
Yes, the correct answer is all of the above. Despite their complex nested mechanics, every single one of those methods ultimately relies on a mathematically known chance of selection at every stage.
And if we look at it from the other direction, all the following are non-probability sampling methods, except T, and the options are things like convenience sampling, quota sampling, snowball sampling, and systematic sampling.
The exception there is clearly systematic sampling. As we establish, systematic sampling utilizes a calculated mathematical interval and a randomly generated starting point. It belongs firmly in the probability bucket. The others do not.
And why are we so obsessed with keeping these buckets separate? Like, what is the ultimate consequence of choosing a probability method over a non-probability method? If a question asks to identify the only sampling method that allows researchers to draw valid conclusions about the larger population, what is the answer?
The only method that grants that power is probability sampling. I cannot stress the gravity of this enough. This is the boundary line of science.
Explain that boundary line for us.
If you conduct a study of 500 people using a probability method, you are mathematically permitted to stand up at a conference and say, based on our data, we conclude that the entire nation of 300 million people experiences this disease at a rate of 10%. You can generalize.
But if you use non-probability,
If you study those same 500 people using a non-probability method, your findings apply only to those 500 people in your room. You cannot mathematically extrapolate your findings to a single person outside of your study. The math forbids it.
that is a devastating limitation. So why would anyone ever use non-probability method?
Usually out of desperation or lack of resources.
Let's look at the worst offender. A sampling method where people who volunteer or who can be easily recruited are used. What is that called?
That is known quite accurately as convenience sampling.
The name is a dead giveaway. The researcher does whatever is most convenient for them, standing outside a grocery store with a clipboard and bothering whoever walks out the door.
Or, as is notoriously common in the field of psychology, a university professor simply mandates that their undergraduate students take a survey for course credit.
Oh man, I definitely took those surveys in college. I was part of a convenience sample.
We all were.
But clearly a room full of 19-year-old college students sitting in a lecture hall in a wealthy Western nation does not represent the emotional or psychological reality of the entire human race.
Exactly. This actually caused a massive reckoning in psychology known as the weird problem, an acronym pointing out that decades of behavioral science were based entirely on people who were Western, educated, industrialized, rich, and democratic. They tried to draw universal conclusions about human nature from the most bizarrely specific convenience sample imaginable.
That perfectly highlights the danger. Let's look at another one that tries to disguise itself as rigorous. Which of the following statements is true about non-probability sampling? The true statement is that quota sampling is a type of non-probability sampling.
Yes, quota sampling is a type of non-probability sampling, and it is incredibly insidious because it mimics the language of probability.
Right, it sounds a bit like stratified sampling. In quota sampling, a researcher might say, my quota is that I need exactly 50 men and 50 women for this market research. That sounds exactly like creating strata. What is the fatal difference?
The fatal difference is how you fill those buckets. In stratified probability sampling, you get your 50 men by randomly pulling numbers from a master list of all men in the city.
And in quota sampling.
In quota sampling, you just walk into a shopping mall and grab the first 50 men you bump into until your quota is full, and then you stop. There is no master list, and there is absolutely no random selection. It's just convenience sampling with a numerical cap.
Which perfectly sets up the trickiest scenario in this entire discussion. Let me lay this out. A researcher planned a cross-sectional study to assess the level of satisfaction of patients attending a clinic. For this, the researcher selected the first 100 patients who visited the clinic, starting from a fixed date. What type of sampling is mentioned in this case?
This scenario catches a lot of people off guard. The correct classification for this is purposive sampling.
See, my instinct is to call that convenience sampling. They just sat at the front door and grabbed the first 100 people who walked in. Why isn't it convenience?
It walks right up to the line of convenience, but the key is the rigid, deliberate constraints the researcher applied. They didn't just take whoever was around whenever they felt like it.
Right, they said starting from a fixed date.
Exactly. They intentionally set a specific, unyielding parameter, the first 100, from a fixed date. They had a specific design purpose in mind for that exact time frame.
I see. So if patient 101 walks in, they are deliberately excluded because the purpose has been fulfilled, or someone usually comes to the clinic on Thursdays, but the fixed date was a Monday, they are structurally excluded.
Exactly. The researcher applied a non-random, human-designed quota and timeline to fulfill a specific clinical purpose. Because they aggressively shaped the parameter rather than letting a random system dictate it, we classify it as purposive.
Okay, so why are we so universally hard on these non-probability methods? It ultimately comes down to the most toxic word in science: bias.
Yes.
Let's look at a fundamental truth about probability. Random sampling in probability samples reduces the possibility of selection bias. True or false?
That is unequivocally true. Randomness is the ultimate weapon against selection bias.
And we can look at a specific, fascinating type of bias to understand how powerful randomness really is. If a question asks which bias is prevented by an appropriate sampling technique, the answer is volunteer bias.
Yes. An appropriate random sampling technique directly prevents volunteer bias.
I love talking about this because it gets into human psychology. Why do we care if people volunteer? Isn't it a noble, helpful thing to participate in science? Why is it a bias?
Think about the psychology of online restaurant reviews on platforms like Yelp. Who actually takes 15 minutes out of their day to sit down and write a review?
Oh, it's usually the person who had a transcendent, life-changing culinary experience, or the person who found a dead cockroach in their salad and is furiously, intensely angry.
Exactly. The 80% of people who went in had a totally fine, remarkably average sandwich and went home. Do not log on to the internet to write a review.
Right, the sandwich was adequate. 3 stars. Nobody writes that.
That is the essence of volunteer bias.
Yeah.
People who voluntarily self-select to take a survey, answer a poll, or join a convenience study usually have strong polarized opinions.
Or they have unique underlying motivations. Or they simply have vastly more free time than the average working person.
They are the loud, anomalous minority. If you rely on convenience or volunteer sampling, your data will scream that the world is filled with extremists because you have completely missed the silent average majority in the middle.
This is blowing my mind because it explains so much about modern internet polls, but how does probability sampling actually fix it?
If you use an appropriate probability technique, say simple random sampling from a national database, you are forcing the selection. You use a computer to generate a random phone number. You call that person.
So you're basically hunting down the average person.
You have essentially forced the silent average person in the middle to give you their data.
Yeah.
You aren't waiting for the angry people to come to you. You are blindly piercing through the population. That is how randomness crushes volunteer bias.
And by crushing that bias and maintaining the strict mathematical laws of randomness, you unlock the final, ultimate superpower of probability sampling, the ability to calculate your own ignorance.
I love that phrasing, calculating your own ignorance. That brings us to our final two concepts, which are so foundational that the curriculum basically tests the exact same concept twice to ensure you understand it.
Let's look at them. The first asks us to identify the correct statement regarding sampling error, and the answer is that the magnitude of error can be measured in probability samples.
Yes.
The second is a true-false statement. The magnitude of sampling error can be measured in probability sampling, and the answer is, of course, true.
Yes. The magnitude of error can be measured in probability samples, and it is absolutely true. This is the mic drop of statistical science.
Walk me through the sampling error concept, because it sounds like a mistake. Like, did the researcher drop the test tubes?
No, it's not a mistake by the researcher. Sampling error is the natural, unavoidable mathematical discrepancy between your tiny sample and the massive true population.
Okay, explain that.
Remember the soup analogy from the beginning?
Yeah.
Your spoonful might have exactly 4 pieces of carrot in it. Does that mean the giant vat has exactly 4,000 pieces of carrot? Probably not exactly. There is a slight natural variance. That variance is the sampling error.
Okay, so how do we measure it?
Because probability sampling is based on strict mathematical laws, the normal distribution, standard deviations, we can run a formula at the end of our study to determine exactly how wrong our estimate might be. We can quantify our own uncertainty.
Oh, this is what you see in the news every election cycle.
Exactly.
The latest poll shows the candidate leading with 52% of the vote with a margin of error of plus or minus 3%.
Yes. That plus or minus 3 is the calculated magnitude of the sampling error. The pollsters are mathematically proving the limits of their own uncertainty. They're saying, we are highly confident the true number is somewhere between 49 and 55.
And this is the critical, absolute final takeaway of this entire deep dive. You can only do that math if you used a probability sample.
Precisely.
Yeah.
If you used convenience sampling, if you just put a poll on a website and let angry people volunteer to click it, the mathematical formulas do not work. Your margin of error isn't 3%. It is entirely, utterly unknown. You could be off by 2% or you could be off by 40%. You have absolutely no idea how wrong you are.
Wow.
So it is a foundational truth of research that the magnitude of error can only be measured in probability sampling.
Okay, we did it. We just took 30 complex, deeply academic scenarios and reverse engineered the entire philosophy of scientific observation. We transformed them from textbook jargon into a logical, practical toolkit for understanding how the world actually works.
It really is an incredible journey when you lay it all out. It's
Yeah.
a journey from chaos to order.
Because the universe is messy, right?
Very messy. Human populations are infinitely complex and practically invisible in their totality. But with these tools, from defining the rigid sampling frame to executing the gold standard of simple random sampling, scaling up with the genius of multi-stage sampling, and relentlessly defeating volunteer bias, by submitting to the math of probability, we can actually extract universal meaning. We can find the truth.
We started this deep dive with a promise. I promised that you wouldn't just know what the correct answers were, but that you would profoundly understand the why and the how behind them, the mechanics of the truth. And I think we've delivered on that mission. But before we let you go, our resident expert has one final provocative thought for you to carry into your day.
I do. Next time you are scrolling through your news feed and you see a bold headline screaming 70% of people believe X is destroying society, I want you to pause. Don't look at the 70%. Look at the bottom of the article. Look for the fine print and ask yourself, how did they sample them?
Such a good point.
Were those people randomly selected from a valid sampling frame using stratified or multi-stage techniques? Did they calculate a margin of error? Or were they just 1,000 extremely angry people who volunteered to click a link on a politically charged website.
It changes everything.
It does. The percentage doesn't matter if the method is flawed. The method is the actual message.
If they didn't stir the soup before they took a spoonful, well, you really shouldn't trust the taste. Thank you so much for joining us on this custom deep dive. This exploration of the mechanics of truth was built just for you, to empower you to look past the numbers and never be fooled by a bad statistic again. Keep questioning the methodology, keep learning, and we will catch you on the next deep dive.